Hello, everyone, and welcome to our very first Doctor Data Science. The idea behind this is we want to talk about everyday data science topics, questions we see on our community with you guys. This session will be every third Wednesday at 9 a.m. Pacific and 12 p.m. EST, and all the sessions will be recorded and posted on YouTube. I will post this playlist link in a chat in some time. You will see these recordings probably in 24 to 48 hours. So today we have our own Stephen Hillian, Director of Data Science at TIBCO, who is going to talk about how do I pick the K in K-means. Stephen, floor is yours.
Great. It's great to be here. And in case you're wondering who is Dr. Data Science, I like to think that Dr. Data Science is really sort of the sum total of the data science team and our expertise here at TIBCO. It's great to be having our inaugural session today. And the way we're going to do this is every month we're going to have a little nugget of information at the beginning, sort of a commonly asked question in data science. This week we're going to be focused on how we optimize the value of K and K-means. And then we'll have sort of a featured topic which will take up most of our time. And today we're going to be talking about deep learning and when that's useful and maybe when it's not so useful. And then we'll have a little bit of Q&A at the end where maybe you have asked some questions which you can submit through the Q&A button. Try not to use the chat window, but use the Q&A button instead. And we'll also pick some questions that are particularly popular and upvoted or widely viewed on the TIBCO community. So we start off with our little information gain session, as I like to call it. So this is where we're going to gain some information about data science. And the question that we're answering is how we pick the K in K-means. We all maybe are familiar with K-means clustering, but you have to specify a K when you build your clusters. And how do you know which value to specify? Well, maybe the best answer, I think, just based on my own experience and talking with the team, is that you kind of want to know what K is in the beginning. If you can possibly have some intuitive sense of what K should be or around the place to start, then that's really ideal. We were working on a project. Actually, this is one that Nico worked in. Nico is one of our data scientists on the team. He's actually joining me today because he worked on the deep learning project. Hey, Nico, thanks for joining us.
Hello, great to be here.
So yeah, one of the projects that Nico worked on was for analyzing the motion of commuters in a particular area and trying to identify what mode of transport they were using. And I guess in that case, right, Nico, you knew what K was, right?
Right. In that case, we had three very defined instances of what K could be or what the transportation could be. Would it be a car or a train or walking? So in that instance, K would be 3.
Yeah. So that really helped in that particular case, and we were able to pin down pretty accurately, actually, which modes of communication based on people's cell phone signals. Another example that we have from some of the projects with TIBCO is looking at wafer maps. These are wafer maps that come off the factory floor from high-tech manufacturers, right, who are making silicon chips, who are making these die that come on these big silicon wafers. And you have these patterns of failures and successes. So you look at this set of wafers that we have here on this slide. You've got cluster number 3 is pretty good. Cluster number 17 looks like a disaster. But these are different patterns, and we analyze these patterns using a variety of different encoding techniques for encoding images. But we don't know how many different types of patterns you're likely to see from failing wafers on a floor. So that's a much more difficult case where you really genuinely don't know what K is going to be. So what do people do in this case? Again, I was asking around the team, and certainly the most popular answer was to use a sort of elbow plot where you plot some sort of indicator of the quality of the clusters on the y-axis and see how that changes over time, and look for some sort of elbow where you see sort of diminishing returns. And so the classic way to do it seems is that you compute the sum of the squared distances, so some metric that indicates how far points are from the center of their cluster, how far they are from the centroid. And obviously you want that to be as tight as possible, so you want that to go down. So as you increase K, it is going to go down, but K could equal the total number of points, in which case the the sum of the distances is going to be 0. So you really want that to be going down, but not too much. And you want to look for when you're suddenly seeing less advantage from increasing K. I actually applied this method to the countries data set. So this is a data set, I'm just doing this in TIBCO's data science platform here. Here's a list of countries with some socioeconomic factors. These are a few years old, I think, and we normalize these and build a k-means clustering on those. And then we look at the different iterations of K and see what that sum of squared distances is. And we build that elbow plot there. I don't know about you, I find these elbow plots for a lot of these k-means that I've done in the past, a little difficult to interpret. Where's the elbow here, right? I mean, I guess K equals 3, maybe. I don't know, what would you say, Nico? Where would you say you're seeing sort of diminishing returns?
Yeah, I mean, I would kind of put my money on 3 there, but you're right, it is a little unclear.
Yeah. K equals 3 would support sort of the traditional, sort of the old academic way of grouping countries right into sort of 3 different groups, you know, sort of industrial world and developing world and so on. But then what I did is I used another, so I was asking around the team, and one thing that we used in a project, this was actually for one of those high-tech manufacturing cases, is we used something called the Dunn index. There are these other indexes of the quality of clustering. And the Dunn index, let's see if I can get the explanation for this right. Here it is. We didn't have this in our data science platform, but you can easily add new functions into TIBCO data science by running Python or R code. So I added the Dunn index here and plotted that for different values of K. Before we look at this, what is the Dunn index, right? So let's see if I can get this right. So you take, the first thing you do is you look at your clusters, right? And you take the smallest distance between points that are not in the same cluster. So you look at points that are not in the same cluster and you compute the smallest distance. And if you think about it, you want that number to be as big as possible because you want the clusters to be well separated, right? If you think about what an ideal cluster map would look like, sort of tight groups separated from each other. So you take that smallest distance between points not in the same cluster, you want that to be as big as possible. You take that number, and then you also take a second number, which is the largest intra-cluster distance, essentially the diameter of the cluster. And you want that to be as small as possible because you want your clusters to be super tight and well constrained with points close to each other. So you want that number to be as small as possible. And you take the ratio of those numbers. You take the ratio of the smallest distance between clusters to the intra-cluster distance, the diameter of clusters. And so that's the Dunn index. And if you think about it, you want the numerator to be well, you basically want that Dunn index to be as big as possible because you want the numerator to be big and you want the denominator to be small. Yeah, that's right. So you want the Dunn index to be as big as possible. So I plotted that. Actually, I got some help from Vinoth Manamala on our team. Thanks, Vinoth, for providing these computations and providing the Python code. And so maybe surprisingly, K equals 5. That's what the Dunn index sort of recommends. Which kind of brings me back to my original point, right? So what does that actually mean? Well, I should go back and look at my clusters and see why it might be that by just looking at which countries belong in the same cluster and see whether that makes sense. So I guess it comes back to my first point, which is you kind of want to try and use your intuition and sort of read the data and just use these metrics as sort of a guideline rather than providing a definitive answer. Alrighty, let's move on to our main subject now. Which is about deep learning. And we posed the question just a few months ago in a project that we're working on, a very general question, which is when is deep learning a good method to use? And the reason why we thought this was an interesting question, because we found that deep learning was being used all over the place, right? I would interview candidates for data science positions and they always said that by far the most common algorithm they've been using lately is deep learning, and they applied it here and they applied it there. We also found that a lot of organizations that we worked with as a data science team were insisting that they wanted to use deep learning, and we were questioning a little bit whether that was really a valid approach. It seemed like there was a lot of hype and excitement about deep learning, rightly, because it's a really powerful and innovative method, but maybe it was being a little bit overused. And the extreme example I found here, which I was telling Nico about the other day, we had this financial organization that I worked with a few years ago, and they were doing these stress tests, these financial stress tests, right, to make sure that the banks remain solvent under harsh economic conditions. And they had a data set that looked a little bit like this one that I have sort of in the background here, where they had sort of quarter by quarter these macroeconomic indicators, and then they had their own internal indicators of, you know, the total value of accounts held by the bank and volatility and the number of customers and all these internal factors. And they wanted to apply deep learning to predict the assets under management for the bank to see what would happen if they, if suddenly macroeconomic factors headed south. And that seemed crazy to me because if you think about it, right, these are just quarter by quarter numbers. I think they had something like 15 years of data, so about 60 rows of data. I mean, building any model on that is going to be challenging, I think. You know, how big is your holdout sample going to be with just that small number of rows? But deep learning, at least my intuition was that it really worked much better on larger data sets. And also, don't you want some intuition about which macroeconomic factors are most affecting your bank? So are you really going to get that from deep learning? So examples like that and just the sort of a little bit of the hype around deep learning caused us to ask this question, you know, is deep learning really good for all these implementations? And I did a little survey around, just talking to some folks and just doing online research. And we found that the conventional wisdom around deep learning is as follows, right? There are lots of great things. It works great on really complex data like image data and text data, speech data. It's a really innovative, hot area, so that makes it cool. And it also means more legitimately, right, that, you know, there's a lot of new capabilities being invented every day. And so you sort of want to stay abreast of that and take advantage of all those innovations. One arguable pro, right, is that it reduces feature engineering because essentially these neural networks create the features internally themselves. And so that, you know, you can just throw your entire data set in and let the deep learning models build the features themselves. And also there's really great open source support for deep learning these days. The obvious example being TensorFlow, but there are others as well in the standard sort of Python library. So lots of great reasons. But the cons are, the conventional wisdom again seems to be, well, it needs a lot of data. It's really complex. There are a lot of, you know, how do you define all these hidden layers? There's really complex parameters and don't seem to be really great best practices around this, at least not that I'm familiar with. And also, I think a lot of people will point out, right, the model structure is really opaque and really, you know, what are all these hidden features? What sort of scary things are being hidden within the structure of the model? And another argument that I've seen people make is that they're really computationally expensive. I think one of somebody in our data science team shared this on Slack the other day that, you know, we make a significant contribution to greenhouse gases just from the energy expended in running these calculations for these really huge deep learning models on really huge data sets. So the project that we worked on was essentially to say, well, can we test out this conventional wisdom, right? Is it really true that small data sets don't work so well, that these are hard to use and so on? So this is a project, we actually made an intern project for one of our interns, Adam Faskowitz, and Adam actually is going to be joining us full time this year, which we're really excited about. And he was helped by Nico. So Nico, this was late last year, right? You worked on this project or last summer?
Yeah, it was over the summer with Adam. And I'd like to give a big shout out to Adam. I think he's on the call, but he did great work on this, and it was fun working with him on this.
Right. So my understanding of the method you used, right, is that you wanted to compare deep neural nets. So we focused really on classification tasks, and we sort of took the standard, sort of the usual suspects when it came to classification models, gradient boosted trees, random forest, SVM, and logistic regression. We want to make sure, right, there are sort of default parameters that you tend to use for these things, right? The default number of trees or default lambdas, whatever, with logistic regression. So how do we deal with that? You said we used a grid search for managing the parameters. Can you explain that a little bit more, Nico?
Right. So, well, first off, we took all these different algorithms and we wanted to compare them against each other in different use cases. So how would they perform for looking at fraud or spam emails, phishing emails? You know, we even actually used an image data set because we really wanted to get a holistic view of, you know, where do these algorithms work and for what use case? So as far as the parameters go, Stephen, you're right. They do have sort of default parameters, right, where you can more or less just set them up with without really doing much and just let them run. But what we also wanted to do was look at, okay, well, if you actually spend a little amount of time fiddling with the parameters, known as hyperparameter tuning, how much impact would that have on the model and how much better would it make it? So, you know, there's a number of different ways to do that. Probably Well, the simplest way is just to, randomly type in different parameters and see what happens. A more sort of, if you will, scientific way is known as grid search, which is where you basically set up an array or vector of these parameters, and you basically just set up a for loop, right? So you go through all the combinations of all the parameters that you set, and you run and train the model many different times, sort of just comparing the results from each parameter to each parameter. So that's what we did for these models.
And despite that, you mentioned you applied that to a few different use cases. We'll talk about those in a second, but how did you then evaluate the models? Use different accuracy metrics, right?
Right. There's a lot of different types of accuracy metrics. Yeah. We kind of defaulted to, what does the industry say is the standard accuracy metric? Yeah. Right. Something for a rare event like predicting fraud, you're going to have a different accuracy metric for that than, say, classifying what type of object in images. And the reason for that is, really, if you're dealing with a rare event and, 99% of all your events are non-fraudulent and then 1% are fraudulent. Well, even if you train a model that, it might say it's 99% accurate if it just predicts that everything is non-fraudulent. So the two main metrics we used were area under the curve for ROC, and then we also used just a straight up accuracy metric. So how many
F1 score or something like that?
Yeah.
Right. Okay. Great. That makes sense. What I liked about this project, right, is you didn't just look at the accuracy, though, right? You also looked at performance and ease of use. I don't know quite how you measure performance. Seems easy, right? Just see how long does it take on sort of the same hardware. But what about ease of use?
Yeah, I would say ease of use is probably the most rigorous part. We use the I index, which is the intern index. It was really, what did our intern Adam say how hard this was to set up, right? So somebody coming in, bringing in this data, setting up these algorithms, how hard was it to get a workable model? Right. And how we'll see a little later, I think, with some of the data, but the more work you put into it, how much value did you get out of that?
In terms of accuracy, I see. So there's some objectivity, right? It's like you have a lot of parameters, but do you actually get a bunch more accuracy by tweaking those? Yeah.
For sure. Yeah, exactly.
Great. Okay, well, let's dive into the results then. So these are the data that we used, right? So we've got some data sets with sort of increasing number of rows there, going up to about 1.5 million, and different numbers of features. So we've got 784 for the FMNIST. So these data sets, people might be familiar with these. Lending Club, I think, is a pretty well-known data set. There's a standard sort of customer churn data set that we got from Kaggle, UC Irvine. There's the website phishing. Tell us about the FMNIST. Everybody knows about, well, maybe not everybody, but MNIST is a pretty commonly used data set. It's like looking at handwriting, looking at letters and the images of those. So it's an image recognition stuff. What's FMNIST?
Yeah, FMNIST is basically the same type of data set, right? It's a data set with a bunch of images, the same size as the traditional MNIST data set with the handwritten digits. But instead of digits, it's actually articles of clothing, right, or fashion. So there's shoes and shirts and hats and all sorts of stuff. So it's the same, I think, 28 by 28 pixels, grayscale image just of articles of clothing.
Got it. Cool. Okay, great. So looking at the results then, so I've charted these on a zero-based axis for honesty, but so it's a little difficult to see the differences between these, but there are winners here. Random forest and gradient boosting generally did best, I think, on almost all of the tests. I think deep learning did best on the image recognition, maybe not surprisingly. But at least based on this sort of not completely scientific survey, but still sort of objective, looking at these accuracy metrics, seems like gradient boosting, random forest, these ensemble methods are working pretty well across the board. Would you say that's true?
Yeah, I would. This is a graph that shows overall accuracy, but there's definitely a story behind the accuracy, right? Yeah. And I think we'll get into that, which is these algorithms do better with different tasks and different amounts of effort put into them. So,
Yeah, so let's get into that actually. Well, one thing you mentioned about, right, as we tried all these different hyperparameters, away from the defaults, right, we found that you got different boosts in terms of the quality improvements. I thought this was interesting. There's lots of questions around this, actually, and we don't have time for this. I was a little surprised, particularly by the regression. I don't know if we tweaked like regularization parameters, but not much improvement from tweaking the parameters. This is percent improvement, right? So it's pretty tiny in any case. But the random forest, you get a lot of improvement just by tweaking the number of trees and the depth of the trees and stuff like that.
Mm.
But anyway, these are the overall conclusions that that the little team came up with. I think these make sense to me, and they, you know, in a sense, they just confirm the conventional wisdom, but it's nice to see that conventional wisdom being confirmed, right? It's like deep learning really does not perform that great on small data sets. The random forest and the gradient boosting did far better, right, Nico? And on large data sets, you know, those three there did well. Performance was kind of particularly good for random forest and deep learning on large data sets. The small parameter space, the number of things you have to, this is the sort of subjective intern index that you're talking about, like how easy was it to use? And perhaps not surprisingly, we found regressions are pretty easy to tune.
Mm-hmm.
You know, basic, not too much to tune there, say some regularization parameters. That deviance from the default as you tweak them. So what's the payoff from tweaking those, right? You get quite a bit of payoff from the random forest to deep learning in the SVM. Perhaps not too surprising there either. And how easy it is to interpret the model, right? Of course, is a big deal, right? And I think most people would agree regressions, you know, logistic regression, linear regression, very easy to interpret. Deep learning on the other end of the scale. Random forest, how would you justify that? Why is random forest sort of easy to interpret, Nico? What else would you say about this table?
Yeah, well, for random forest, I think one of the best things you get out of it is you get a list of variable importance, right? So for each of your features, you can kind of tell which feature had the most impact on determining the output. So that's something. And then also, you know, you can actually look at, if you don't have too many trees, you can actually look at the trees that the random forest generates. And, you know, that is really interpretable. So I think random forest is definitely an interpretable model here.
Yeah, certainly more than I would say deep learning.
Right. Yeah. I mean, one other thing I'd point out
yeah.
here, Stephen, is, you know, if we think back to that accuracy chart, you know, gradient boosting was overall the winner. But one thing I'd like to point out here is that it really does not have good performance in terms of timing, right? Especially as your data sets get larger and larger. I remember the timing for gradient boosting just, you know, exploded compared to the other models. So yeah, it did better in terms of accuracy, right? But if you don't have the time to train the model over and over again, then gradient boosting might not be the one for you.
Yeah. Great. Well, I like this little project. It's a very nice idea to investigate. And again, even if the conclusions mostly just confirmed conventional wisdom, I think that's a really useful exercise, because I know I often say to people, like, you know, maybe don't start with deep learning, especially if your data set's a little smaller or if you don't have a ton of features, and especially if you want something interpretable. And that's maybe sort of a boring thing to point out, but I think it's important, and I think it's nice to see this confirmed by this informal test here. So nice job.
Yeah, and one other thing, if I could add, I mean, I know before I got into data science, just sort of going off of what you were saying, I thought one of the most interesting things was about the FMNIS data set, right? I was saying before I got into data science, it really seemed like deep learning had a monopoly on image classification and you know, that sort of area, which is, you know, somewhat true, right? It did perform the best, and that's really what it's good at and excels at.
Right.
But one thing to point out is, you know, random forest and gradient boosting, and actually even the SVM did pretty well on the image classification test, which is just, I think, interesting on my part, which is that you don't always need to turn to deep learning to work with some of these more complex tasks. Gradient boosting and random forest especially are pretty versatile and can be used for many different things.
Yeah. Great. Good. Well, let's move on. Getting close to the finish here. It's such a short session, but lots of interesting stuff to talk about. Next month, we're going to be talking about featurization of text data. So, you know, you have methods like word to vec, various statistics that you can compute when you're analyzing text and taking raw text data and turning that into a structured format so that you can then perform analysis on it, whether that's clustering or predictive models or whatever else you might want to do with text. And so there are standard methods for adding structure to text data, and we want to talk through those and talk about the pros and cons and understand how to do them and maybe different ways to use different tools to do that efficiently. So that should be an interesting topic. Text analysis, of course, something most people have to do at some point in their lives, and it's good to know sort of what the state of the art is. So we'll be focusing on that next month for our featured session. We'll also have another info gain session, a little tip or trick, much like we did with the k-mean stuff, and so we'll have one of those next month as well. So let's wrap up now with a few question and answers. And so what we did is we took some of the questions that have been submitted recently on the TIBCO community around data science and analytics. We picked off 3 that we thought were kind of interesting to mention to folks on this call. And so let's just quickly go through those. And if you have additional questions, we'll cover those either in the next session or after this session once we've finished the formal recording. So we've got 3 ones here. So how can we use or integrate Spotfire? So Spotfire, of course, is the dashboard visualization and exploration application that TIBCO produces. How can you integrate that with Team Studio? Team Studio, in case you're not familiar, is that data science platform that I was just showing you before that I use just for running some of those k-means. It scales well. It's a web-based or collaborative app for doing data science. So you have the Spotfire, which is more focused on the front end and the visualization, and Team Studio on the back end for manipulating large data sets and doing data science. Then those be integrated. And this is a common question because those products were not always integrated in the past, but now they are. You can actually run deep analyses with Team Studio in the background and visualize the results from Spotfire. You can do that with all of the TIBCO data science products. And that's documented on, let me just click this here. And so there on the TIBCO community, you can see there's this new data function. This got released. When did this get released, Nico? It wasn't that long ago, right? In last year, I think.
Yeah, certainly. I think within the last 6-8 months, maybe.
Yeah, great. So that's really cool. So you can, as this little image sort of indicates here, you can run visualization with Spotfire, which actually are using the outputs of a modeling operation that's developed in that visual analytics environment that I was talking about before. So that is actually available for you to download on the TIBCO community so that you can actually integrate your Spotfire presentations with TIBCO data science. Here's a second question here. Can TIBCO data science connect to Azure Data Lake? This was actually recently submitted, and the answer is yes. We can support Azure data warehousing and all SQL Server operations. So there's actually a list of supported platforms for TIBCO data science in the documentation that's searchable online. So you can just Google that for supported platforms for TIBCO data science, and you'll see that Azure is listed there. And in fact, there's a whole host of big data and cloud data sources that we now support. HD Insight is coming up soon. We have Dataproc from Google that we support, EMR from Amazon, Redshift, BigQuery, and so on. So you can see all those listed there. And then finally, hey, Nico, you might know something about this. You can use PySpark in TIBCO data science, right? If you want to have scalable Python routines run from within that same collaborative environment. I actually, in this done index, right, you can see that I'm running Python here, and this can be PySpark code. Is that right, Nico?
That's right. And you get really highly scalable notebooks as a result.
Cool. So those are some highly viewed questions that are on the TIBCO community. If you've got other questions, I think we might stick around after the formal session to answer those. Ninad, any other closing remarks?
No, that was amazing session, guys. And everyone, we are going to talk about such interesting topics every month. So as I mentioned, every third Wednesday at 9 a.m. Pacific or 12 p.m. EST. So that's it for today. Thank you for joining in and talk to you guys next month. Thank you.
Great. Thanks, Ninad.